Introduction to Bitcoin Proof of Work. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with a focus on networking. Also, hit the bell icon to get notified of new videos. Today, we are exploring Bitcoin Proof of Work through the key questions and insights from an in-depth discussion. We will focus on the core concepts that explain how Bitcoin achieves consensus without central authority, covering transaction flow, the mining puzzle, and why computational work secures the network. What is proof of work? Bitcoin proof of work is the system that ensures everyone agrees on which transactions are valid without needing a central authority like a bank. When people send Bitcoin, those transactions are collected into blocks. Before a block is added to the blockchain, miners must prove they have done computational work by solving a difficult mathematical puzzle. This involves finding a special number called a nonce that makes the block's hash meet certain criteria. The miner changes the nonce and rehashes repeatedly until finding a valid result. Once found, the proof is broadcast to the network where other nodes can easily verify it with a single hash calculation. This asymmetry between difficulty of finding versus ease of verifying is fundamental to security. Finding the solution requires billions of attempts, but verification is trivial. The winning miner earns new Bitcoin as a block reward plus transaction fees. This provides security because rewriting blocks would require redoing enormous computational work, making attacks prohibitively expensive. It ensures fairness through open competition based on computing power, and maintains decentralization because the network agrees on the longest valid chain representing the most accumulated work, with no single entity deciding what is true. Block construction timeline. A crucial question is whether miners can start a new block before solving the puzzle. The answer reveals Bitcoin's timing mechanism. The block is actually constructed first, then miners start solving the puzzle. Here is the sequence. Miners gather unconfirmed transactions from the mempool, the network's waiting area for pending transactions. They build a candidate block containing these transactions, a reference to the previous block's hash, and a nonce field. Only after building the block do miners begin solving the cryptographic puzzle by changing the nonce and hashing repeatedly until finding a valid hash. So the puzzle is solved after block creation, not before, and the block does not become official until a valid hash is found. Miners cannot move to the next block until someone in the network finds a valid solution for the current block height. All miners worldwide work simultaneously on the same block height, racing to find the winning solution. When one miner finds the correct hash, everyone verifies it quickly and starts building the next block using the newly accepted block's hash. During this time, transactions continue flowing into the network and are stored in the mempool. Miners continuously update their candidate blocks with new transactions to maximize rewards. If the puzzle takes the target 10 minutes, new transactions queue up waiting for the next confirmed block. Transaction distribution. Understanding how transactions move from mempool to blocks reveals Bitcoin's decentralized nature. Transactions do not go to a single miner. No miner owns or is assigned specific transactions. When you broadcast a Bitcoin transaction, it spreads peer-to-peer across the entire network. Every full node that receives it verifies the transaction by checking signatures and balances, and if valid, adds it to its local mempool. Since every miner runs a full node, they all see roughly the same mempool, though it might differ slightly due to network latency or local policies. Each miner independently decides which transactions to include in their next candidate block. Miners are motivated by profit, so they sort transactions by fee rate in satoshis per byte and fill their blocks with the most profitable transactions first, up to the 1 megabyte block size limit. While most miners pick from the same pool, their blocks might differ based on which transactions they heard first, fee priorities, or policy filters. When a miner finds a valid hash and solves the proof of work, they broadcast their completed block with all chosen transactions. Other nodes verify the proof of work is valid. Transactions are valid with no double spends, and the block links properly to the previous one. If everything checks out, nodes accept the block, add it to their blockchain, remove those transactions from their mempool, and start mining the next block. Simultaneous block discovery. Sometimes two miners find valid blocks at almost the same time, creating a temporary fork. This is natural, and Bitcoin handles it elegantly. When this occurs, some network nodes see miner A's block first, while others see miner B's block first. Both blocks are valid and reference the same previous block, so, for a brief time, there are two competing blockchain versions circulating. Miners then start building on whichever block they received first, creating two separate chains temporarily. Eventually, one chain becomes longer because one of the miners building on it finds the next block first. Bitcoin's consensus rule states that the longest valid chain is authoritative. So, when one chain gains a block and becomes longer, the entire network converges on that version. The shorter chain's most recent block becomes orphaned, and any transactions unique to that orphaned block that were not included in the winning chain return to the mempool, where they will be picked up by future blocks. This longest valid chain rule keeps the network consistent over time, despite its distributed nature. It is also why we wait for multiple confirmations on important transactions. Each additional block built on top makes it exponentially harder for a reorganization to occur. A transaction with one confirmation could theoretically be reversed if its block becomes orphaned, but after 6 confirmations, the amount of work required to reorganize the chain becomes practically impossible without controlling majority network hash power. Why computational waste matters. One of the most insightful observations is that when one miner solves the puzzle, all other miners' computational work goes to waste. This seems incredibly inefficient. Most miners' computations are not reused when they lose a round. They simply start over on the next block. This is exactly why Bitcoin mining consumes so much energy, because it relies on real computational work to secure the network. But this apparent waste is essential to Bitcoin's security model and fairness. Mining operates like a lottery where each hash attempt is a ticket with a tiny chance of winning. The more computing power you have, the more tickets you get per second. You might lose many rounds consecutively, but statistically your share of wins matches your share of total network power. This is why miners join mining pools, grouping together to share rewards proportionally when any member wins, smoothing out randomness with small, steady payouts instead of rare, large wins. When a miner loses because someone else solved first, their block template becomes obsolete since the blockchain advanced. They immediately discard it and build a new block referencing the latest one. Their transaction collection and validation logic are reused instantly, but the hashing attempts are discarded. This waste is essential because it ensures adding a block requires real cost in electricity and hardware, preventing anyone from cheaply rewriting history. To change one block, an attacker must redo all work done after it, faster than the rest of the network, which is practically impossible. This creates economic fairness where everyone can join, but rewards match real contribution. The mining competition. The mining competition showcases how Bitcoin achieves consensus through computational racing. Thousands of miners worldwide work simultaneously, creating the next block. They see roughly the same mempool transactions, so their candidate blocks are quite similar, though not identical, due to different selections or network timing. Every miner starts solving the cryptographic puzzle for their candidate block, competing to be first. Modern mining operations use specialized ASIC hardware, performing trillions of hash calculations per second. Each hash attempt is a guess where the miner changes the nonce in the block header and computes the hash to see if it meets the difficulty target. If not, which happens almost every time, they increment the nonce and try again billions of times per second. The first miner finding a hash meeting the difficulty requirement wins the round and immediately broadcasts their winning block to the entire network. Other miners receive this block, quickly verify its validity, and then immediately stop working on their own candidate block for this round. This is crucial because the blockchain advanced with a new accepted block, so all other miners must abandon their current work, acknowledge the winner, and start building a new candidate block on top of the newly accepted block. This is how consensus is reached organically without voting, coordination, or central decision makers. The proof of work itself, the valid hash meeting the difficulty target, is self-evident proof that computational work was performed, and other nodes can verify this instantly. The cryptographic puzzle explained. Understanding the puzzle itself is crucial to grasping proof of work security. The puzzle is a hash challenge where miners compute a hash, a fixed-length digital fingerprint, using the SHA-256 algorithm applied twice to the block header. The puzzle asks miners to find a number, the nonce, such that when the block header is hashed, the result is numerically smaller than a specific target value. Mathematically, the hash equals SHA-256 of SHA-256 of block header, and this hash must be less than the target. The target is a huge 256-bit number. The smaller the target, the harder the puzzle, because fewer possible hashes will be below it. Bitcoin adjusts this target roughly every 2016 blocks to maintain an average 10-minute block time. Because SHA-256 behaves like a random number generator with no way to predict outputs without computing them, the only solution method is trial and error. Miners must change the nonce and hash billions of times until finding a valid result. The block header contains the previous block hash, linking blocks into a chain. The Merkle root, summarizing all transactions compactly. A timestamp, showing current approximate time. Difficulty target bits, encoding the target. And the nonce, which is the only field miners repeatedly change. This is called proof of work because once a miner finds such a hash, it proves that they performed a massive amount of computation. Finding it is hard, requiring many random guesses, but verifying it is easy, as everyone else simply runs one hash and checks if it is below the target. Block header components. The block header is an 80-byte data structure that miners actually hash, and understanding its components reveals Bitcoin's elegant design. The header contains 6 fields committing to all essential block information. First is the version field at 4 bytes, indicating which consensus rules this block follows, allowing for protocol upgrades over time. Next is the previous block hash at 32 bytes, containing the SHA-256 hash of the previous block's header. This is the fundamental blockchain link. By including the previous block's hash, each new block cryptographically commits to all history before it, making it impossible to alter past blocks without breaking the chain. The Merkle root, another 32-byte field, is particularly elegant. Instead of including all transaction data directly, Bitcoin uses a Merkle tree where all transactions are hashed in pairs recursively until you get a single root hash. This allows the header to remain small while still cryptographically committing to every transaction in the block. The timestamp is 4 bytes recording approximately when the miner started working on the block. It doesn't need perfect accuracy but must be within a reasonable range. The difficulty bits field, also 4 bytes, encodes the target value in compact format, telling miners and validators how difficult the puzzle was. Finally, the nonce is the 4-byte field that miners modify while searching for a valid hash. Since it's only 32 bits, it can represent about 4 billion different values, which modern mining equipment can exhaust in fractions of a second. When miners run out of nonce values, they modify other fields like the timestamp or adjust which transactions are included to get a fresh search space. Difficulty adjustment. Bitcoin's difficulty adjustment is one of its most ingenious features, maintaining consistent block times despite dramatic changes in network hash power. When Bitcoin launched, people mined with regular CPUs. Today the network's hash rate is measured in hundreds of exahashes per second, quintillions of calculations every second. Despite this million-fold increase, blocks still arrive approximately every 10 minutes on average. This works through automatic difficulty adjustment every 2016 blocks, which should take exactly 2 weeks if blocks come every 10 minutes. The network examines how long those 2016 blocks actually took. If they were found faster than 10-minute average, There's too much computing power relative to difficulty, so the network increases difficulty by making the target smaller, meaning miners need to find rarer hashes. If blocks took longer than 10 minutes on average, difficulty decreases by raising the target, making valid hashes easier to find. This creates a self-regulating system. When Bitcoin's price rises and mining becomes more profitable, new miners join, hash rate increases, and blocks start arriving faster. Then difficulty adjusts upward, bringing block time back to 10 minutes. If price drops and mining becomes less profitable, some miners shut down, hash rate decreases, and blocks take longer. Then difficulty adjusts downward to compensate. This ensures Bitcoin maintains its predictable issuance schedule regardless of total mining power, like an automatic thermostat keeping the system at the right temperature. The complete mining process. Let's walk through the complete mining process to tie everything together. First, miners gather unconfirmed transactions from their local mempool, selecting those with highest fees to maximize profit. They construct a candidate block containing these transactions, a reference to the previous block's hash to link it to the blockchain, a Merkle root summarizing all transactions, a timestamp, the current difficulty target, and an initial nonce value starting at 0. Now the mining puzzle begins. The miner takes this 80-byte block header and runs it through SHA-256 twice, producing a 256-bit hash. They compare this hash to the target. If the hash is less than the target, they've won and found valid proof of work. But this is extremely unlikely on any single attempt. If the hash is greater than or equal to the target, which happens almost every time, they increment the nonce by 1 and hash again, billions of times per second. Modern ASIC hardware can try trillions of different nonce values every second. When they exhaust all 4 billion possible nonce values, they modify other fields like the timestamp or change which transactions are included, giving them a new search space. Eventually, either this miner or another competing miner finds a nonce producing a hash below the target. That winning miner immediately broadcasts their complete block to the network. Other nodes receive it, verify the proof of work by hashing the block header once and confirming it's below the target, and verify all transactions are valid. If everything checks out, they add this block to their blockchain, remove its transactions from their mempool, and immediately start working on the next block. Conclusion. We've explored Bitcoin's proof of work through the key insights from our discussion. We learned that proof of work requires solving computational puzzles to add blocks without central authority. Blocks are constructed first with mempool transactions. Then miners solve the puzzle by repeatedly hashing with different nonce values. Transactions don't go to individual miners but spread across the network where each miner independently selects which to include based on fees. When two miners find blocks simultaneously, temporary forks are resolved by the longest chain rule. Losing miners' wasted computational work is essential to Bitcoin's security, making attacks prohibitively expensive through real economic costs. The mining competition has thousands racing to find valid hashes first, with winners broadcasting blocks and losers discarding work to start fresh. The cryptographic puzzle involves finding a hash output numerically less than a network-defined target by trying billions of combinations. The block header structure contains 80 bytes of data with previous block hash, Merkle root, timestamp, difficulty, and nonce. Difficulty adjustment maintains 10-minute block times by automatically recalculating puzzle difficulty every 2016 blocks based on how fast recent blocks were found. These concepts form the foundation of understanding how Bitcoin achieves trustless, decentralized consensus through computational work, replacing banks and trusted intermediaries with mathematics and economic incentives. Thank you for your attendance. Please consider subscribing to the channel.